So, one interesting thing, see, I was saying that I was measuring from each loop like this.
Yes.
So that means I place these loops, and then from each loop, I need to have 2 wires coming.
Correct.
A lot of wiring involved. So we were thinking, what if I connect to all of them in series?
I was going to say that. Did you connect everything in series?
Yeah.
Like, and then the next one, and the next one, and then
Yeah.
Okay.
So why not do that?
And then you just have 2 wires.
Yeah, I just have 2 wires.
I mean, it might take you longer to actually do it first time.
Yeah.
Right? But then after that, just 2 wires.
Anyway, one loop I had to wind, and each loop I had to wind. So the rest of the wire comes and form the other loop, and so on. It can be a single wire.
Yes.
Probably more reliable also. But the challenge is, now I have one inductance value. Earlier I had, let's say, n loops, I had n inductance values. So I've reduced the number of connections, but I'm into some problem. How will I know that, okay, this loop is getting changed now?
Can you change the number of turns in each one? No, that's not possible, is it? If you're doing it in series, then
we can do, each loop has a different number of turns and then different sensitivity and things like that. But even then, 2 loops together, I mean, let's say 2 bicycle pass through one loop of having less sensitivity. And the higher sensitivity one passes one cycle. You may get confused. So it may be difficult. So what shall we do? This is what I have. Or this much, I've shown the hint now. So, I mean, what we have done is, all the loops I have connected in series. All of them are somewhat identical. In fact, for the design, what we did, its value was about 100 microhenry.
The whole loop.
One loop. So all in series, let's say 5, 3, it will add, and I will have.
100 means with multiple turns.
Yes. I mean, here we had a photograph. No? Yeah. So this one, these 2 terminals, I get 100 microhenry. And when a vehicle passes, I get very small change. Yeah. But it's a resonant circuit, etc. We were able to pick that change.
Yeah.
So now we have these loops in series. All are identical. But what I can do is, let's say I put capacitors in parallel to these loops. That's what we have done. And each loop, it's L1 equal to L2 equal to Ln equal to, let's say, L. Capacitance values I can change them. It's in our hand.
So you are basically literally connecting a capacitor.
Yes. Yeah. So if I do that, each of these loops will have a different resonant frequency. Correct? Yes. So let's say that is
C value.
Yes. This is resonating at F1, this is resonating at F2, this is resonating at Fn, and so on. So now here I will not give a single excitation frequency. I will generate a V in that will have all these frequency components. So sine 2 pi F1 plus F2t plus F and t, and so on. If I have n number of loops, I will have n number of such frequencies. Right? Now what happens is, if you consider, let's say, this excitation, right? For that, this loop will be, let's say if it's ideal situation, I have L and C in parallel, that means the impedance will be, what we are saying is, X. The j omega L or omega L. Sorry. Magnitude is equal to 1 by omega c. Right? These magnitudes are equal, and the current drawn by these two are in 180 degree opposition. So maybe I think the students have done this. Just to simplify, I have a inductor here and a capacitor here. Let's say this is excited at 1 by 2 pi root LC. The resonant frequency. Then the current drawn from this will be, if it's ideal L and C, it will be 0. Correct?
At
Because-
resonant frequencies.
Yes, at resonant frequencies. Because this current is lagging from the voltage by 90 degree. This current is leading by 90 degree with respect to the voltage. They are in phase opposition. These magnitudes of the impedances are same. So ideally this current is 0.
Observators.
Yeah. I mean, the coil will have some small series resistor. Capacitor will have some loss component. So it will not be 0. It can be close to 0. That means the impedance provided by this for this frequency is almost infinite. But for other frequencies, it will draw current.
Yeah.
Correct? So for F2, up to Fn, this is like, okay, pass. Right? It will pass. It will not pass F1 alone. Similarly, other F2, if I have, in the F2 I have in the excitation, will not be passed by this. Every other coil will pass F2.
On F3, F4, and so on.
Yes. So now, let's say it's like this. I'm exciting. I'm looking at the output voltage here. Even for now, let's forget this CS. Let's say I put a resistor to see the output voltage. Okay. So everything is tuned correctly. I have F1, F2, F3. All capacitors are same. I excite. Output voltage will be nothing.
Yes.
Because there is nothing coming out. Correct? Now let's say one vehicle pass through this. Above that loop. That means L2 will change.
Yes.
That means this is not at resonance. Correct?
It will change.
It will change. So the component F2 was blocked by L2 loop. Now it will pass. Suddenly I will see a component in F2. In the frequency F2.
Yeah.
Correct? And if the vehicle was going through this, I will see a component at F1. So I have to measure this and see at each frequencies what is the output.
Yes. And if you have multiple going on all the
Yeah.
frequency at each frequency.
Each frequencies. Yes. So that way, although we have connected everything series, we are still able to resolve this information. So that's a very nice idea.
Very nice.
Yeah.
And so that means in the beginning everything's 0.
Yes. And whenever there is a vehicle, you see a change in output. I have put finally a capacitor here because this is like a low pass filter. Yeah. And at a frequency, let's say I'm measuring up to 200 kilohertz. Something beyond that, I'm not interested. So after that, I want to suppress it. So I put a capacitor.
So, but you said, let's say for the first one,
Yeah.
it's 0 at the first frequency, but then some current passes through.
Yeah.
For the other frequencies.
Correct.
The same for the other ones. So overall, though, you get a 0.
When no object is there.
When no objects.
When there is an metallic part passes through L1, L1 gets changed. So L1 and C1 together, it was suppressing F1.
Yes, it was in resonance.
Yeah.
But
Because
not
the-
anymore.
Not anymore. So now F1 is passed through this coil. F1 is anyway passed through L2 and Ln because they were not at resonance at F1.
Yes. But then those will be giving some output or no? The other parties.
In an ideal situation, see, let's say this is drifted from resonance. These were not at resonance, so they are almost like very low impedance for F1.
Oh, okay. I see what you're saying. Yes.
Yeah, I have it's very, what shall we say, qualitative explanation. Now, to see whether it's correct or not, we have done a spy simulation. Okay. So given these values and etc., we, sweep the frequency from a low frequency to, let's say, 100 kilohertz and looked at how is this V0 by V changes. Okay. So as you can see at F1, there is a very low point.
Yeah.
The impedance is very high there. That's why the output is very low. And for other frequencies as well, they are all not at same height. That I agree.
I think that's what I was trying to ask.
Yes.
That was my question.
Yes. Because there will be some influence of other.
But there's always
there is always a clear
value
at these resonant frequencies.
Okay. Yeah.
And now in the simulation, what you have done is we have changed L1, L2, Ln, etc. little bit. So you see that change in the resonant frequency. Zoom in view is given here.
Yes.
So there's a shift in the resonant frequency.
And that is clear.
That's clear. Yeah. So you see, it was 100 microhenry. We have changed it to almost 12%.
That's very clear.
Yes. Yeah. It's quite clear.
And is there a limit to that change? I mean, I guess the rate of...
so we will have to select F1, F2, F5, etc. such a way that for the object that we are expecting, the change in inductance should not be so big that it crosses the other resonant frequencies. So that we will have to space it correctly. Now, another advantage is, see, you have just one output to measure.
Yes.
So when in the diagram, we had a data acquisition system, right? In the previous case, if I had, let's say, 4 loops, I will have to acquire output from 4 loops.
Separate.
Right? So I have reduced the hardware also here. Correct? So the cost will actually reduce. Right? Only thing is, you will need a slightly specialized excitation to sweep the. We are not.
No. This is just to check.
Yeah,
right?
This is to check.
Yeah.
We are not sweeping the frequency. We are having an excitation exactly at that frequency alone. Now, another aspect is, when there is no vehicle, the whole thing is at resonance, parallel resonance. So the current drawn is very low.
Yes.
And this loop has to be working always, correct? I mean, whether vehicle is there or not, it has to be ready for sense, correct? So it should not draw current.
Which is perfect. Correct. Otherwise, it might get hot or constantly if it's hot outside, those things might affect.
Yes. Also, the power required for measurement will be minimal if you keep it in this way. Right?
For the case with vehicles, what's the measurement unit that you use to measure the output?
So it's
multiple frequencies.
Multiple frequencies. I think I have a diagram. So for the testing purpose, I have used an arbitrary function generator.
Okay.
To generate this F1 plus F2 plus F3.
Yes.
Right. And then I had a data acquisition system with one channel that acquires this waveform and a computer to analyze.
Oh. Okay.
Yeah. Now this the arbitrary function generator is used. Function generator, we know. Arbitrary means it can be arbitrary waveform shapes. So some of all these frequencies may not look like a standard function. So, but this can be realized in different ways. I can have some way to store this data and then output.
All right.
It need not be a function generator itself.
Right.
So this is one test view. You see all the simulation, etc. Nice, but before going into the field, we wanted to check whether is it real. Right. So we made 3 loops, and then the center loop alone, we brought in a metallic object.
Just near the center.
Yeah. So these frequencies that you see corresponds to resonant frequency of 3 loops.
Right.
And you see when an object is introduced to the center loop, you see a shift in the resonant frequencies. Right? So the 43 became 44 kilohertz. So 1 kilohertz change. Yeah, it's a big change. And one thing you noticed is the frequency has increased.
Yes.
So this frequency has increased when a metallic object is introduced, which is also expected. Because when a metallic object is introduced, it's a conductive object. The field produced by eddy current of that opposes the existing field there. Yes, so the inductance is reduced. So 1 by 2 pi root LC.
Okay. Then
L has reduced, so the frequency will increase.
that makes sense.
Yes.
And we talked about this.
Yeah,
before.
correct. In case this was a pure, let's say, ferromagnetic material with low conductivity, then it would have shifted in this direction. Because the mu has increased, so the inductance will increase.
And frequency will decrease.
Yeah.
Inversely proportional.
Yeah. But in this case, anyway, for the vehicle detection, nobody is going to make
Magnetic.
vehicle with. Yeah. Why to spend extra money? Yeah. And there is no benefit also. So then we looked at is the signature has changed. It's almost the same. I mean, bicycle, motorbike, scooter, all of them have very similar.
3 years.
Yeah.
Unique.
Yeah, it's the same. So although the measurement method has changed a bit, the final outcome is same with reduced power because all coils are in resonance, reduced hardware, all those. In fact, while we were testing, some vehicle with this kind of shape, I mean, 2 rear wheels and a front wheel, standard
Auto.
It's not an auto. The wheel is slightly big. You see some people use this to carry. Yeah, I think it's called as a tricycle. Yes. So for that, like you were asking for auto rickshaw, why is it a spike? You were expecting something like this that is seen here.
Oh.
Huh? So because the front wheel is in, then the rest of it is at a height.
Yes.
Unlike auto rickshaw, its metal is very close to the.
Yes. And the wheels are a little bit big as well.
Yes. So the center loop kicks up in this way. The other 2 loops see just the rear wheel alone.
Right.
Just a special case.
Right.
And bicycles and the scooter and so on gives the standard signature that we were expecting.